postdoc working in Professor Viktor Moshakov's group at Kibble-Zurek, Belgium. So I want to thank the organizers for giving me this opportunity to present some of our recent results. So the topic of my presentation is nanoscale assembly of superconducting vortices with the scanning tunneling microscope tip. The experimental work was mainly done at Kibble-Zurek, but we also have some theoretical support from our colleagues at the University of Antwerp. And this is what I'm going to talk about today. So first, I will give a very brief introduction about the vortex manipulation and the local heating effect of the scanning tunneling junction. And then I will introduce the technique we used to perform this research, which is the scanning hot probe microscopy. And then I will show you the experimental and results with some simulations in these two sections, and followed by a calculator. So we know that in superconductors, the magnetic field is only allowed to penetrate into the material in the form of vortices. So a vortex can be considered as a normal state core surrounded by some circulating supercurrents. And the magnetic field distribution and the order parameter distribution can be described by these two important characteristic lengths. So both of them are strongly related to the superconducting properties. So by studying vortex matter, or specifically speaking, by measuring these two characteristic lengths, can provide a lot of information about the superconducting properties. For example, so the shape of the vortex core is related to the Fermi surface topology and the gap symmetry. It can also reflect the crystal anisotropy of the samples and the vortex interactions, and the vortex lattices is also quite different in different kinds of superconductors. In traditional type 2 superconductors, you can observe this triangular vortex lattice, and in some true band or multi-band superconductors, you observe this stripe-like vortex chains, and also in some type 1 superconductors, you can observe these kind of giant vortices or large normal domains. And what's more, the dynamics of vortices also determines the technological application of superconductors. So this seems very important and necessary for us to control and manipulate the vortex matter. And actually, this has already been done a lot, and you have already seen a lot of presentations in the past few days. So, for example, by introducing some anti-doors as strong artificial Pini centers, so we can guide the motion and the dynamics, control the dynamics of vortices, and by coupling the superconductors with some magnetic or non-magnetic materials, you can also control or manipulate vortices. So I will not go to details, but what I want to say is that on single vortex level, actually there are also many techniques proposed to manipulate individual vortices. In the next few slides, I will give you some examples. So the first one is by using this magnetic force microscopy to manipulate the vortices. We know that the MFM can be used to image the magnetic structures, including the vortices. But if you push this magnetic tip close enough to the sample surface, then the magnetic force applied on the magnetic structures or vortices becomes bigger and bigger. And you can use this magnetic force to drag the vortices, as you see here, or even rearrange them to some artificial patterns. And this allows people to study the dynamics of individual vortices, which is impossible if you measure the transport measurements or AC magnetization measurements. So another example is by using this scanning squid microscopy. They can also do something like manipulate individual vortices. What they did is they push this tip directly on the surface of the sample. So by applying a mechanical stress on the sample, they somehow can suppress the superconductivity, and they found that this can attract the vortices around to the position of this tip, which allows them to rearrange the vortices, and like what they did with the MFM. So recently, there's another interesting report, which is about using the laser to manipulate the vortices. What they did is by using a focused laser beam to locally heat up the superconductor, where they can generate a gradient distribution of a temperature, where you see at the center of this laser spot, it reaches the highest temperature and then it decreases. And this temperature gradient will induce a thermal force on the vortex, which will also attract the vortices around to the center of this hotspot. And you see, they can also arrange the vortices to any kind of vortex artificial patterns. They even create a vortex-free area in this mixed state by moving the vortices to this area. So besides these techniques that are used to manipulate individual vortices and to directly realize the vortices, actually there is another powerful technique which is often used to study the vortex method, that is the scanning tunneling microscopy. I think there's no need for me to introduce the power and the ability what the STM can do. So the question is whether it is possible to manipulate the individual vortices with STM like these techniques can do. The answer is yes, but how? So we know that when a tunneling junction is established between a STM tip and a sample, there will be some energy dissipation due to the launch and relaxation of these hot electrons. And the power of this tunneling junction equals IV, where I is the tunneling current, and V is the bias voltage between these two electrodes. And at a constant height between this STM tip and the sample, so the tunneling current is almost proportional to the bias voltage. So if you keep the tunneling current constant, then you see that the power of this tunneling junction is proportional to the bias voltage. So we can control the power of this tunneling junction by tuning the bias voltage. And at the smaller values of this bias voltage, you see that the power dissipated in the two electrodes are almost equal to each other. So by using this STM tunneling junction as a local heater, so we might be able to heat up the superconductor locally, and just like what they did with the laser beam. So and then this will also generate a temperature gradient, which will attract the vortices to this hotspot. But this gives us more controllability compared with the focused laser beam. Actually, this local heating effect has already been used to study many different systems. For example, in this freestanding graphene, so it has some kind of curvatures. So people found that they can use this STM tip to locally heat up the graphene to control the curvature of this graphene. Since the graphene has a negative thermal expansion coefficient, so when they heat up the graphene with this STM tip, the graphene will shrinks. And then if they switch off the turning, then it will expand. And they also estimate the temperature change at the position of this STM tip, which they found it can be up to 200 Kelvin, which is very impressive. And there are also some examples reported by using this tunneling junction to even anneal and crystallize the sample. As you see here, so after applying a tunneling pulse, they see that they can crystallize the material. So now let's see what we can do with this local heater in vortex systems. So the technique we used to perform the research is called scanning Hall probe microscopy, which combines an STM and a submicron-sized Hall cross. So the technique was designed based on the Hall effect. So by measuring this the Hall voltage at this of this Hall cross, then we can estimate the external field through this this Hall cross. But the problem is, in order to have a high spatial resolution, we need to push this Hall cross to close proximity of the sample surface. And to do this, we use STM tip. So we first approach the Hall sensor to the sample until we reach the tunneling current we set, and then we lift the Hall. Then at that time, we know that the course is already very close to the sample surface, and then we lift the Hall sensor about a few hundred nanometers, and then we start to scan. And that's why we call it a non-invasive scanning technique. But now, instead of just using this STM as a feedback to bring this Hall probe to the sample surface, so we will use it as a local heater now. So we are using it to manipulate the vortices to control the superconductivity locally, and then we see what happens with our Hall probe. Okay, this is the experimental results. So this is a vortex lattice observed after field cooling. So we see that the vortices are more or less homogeneously distributed in the scan area. And then we apply a tunneling pulse. And so after switching over the tunneling, we scan the same area again, and we see that there's a cluster formed. So this means the local heater works. So this means that by using this STM tip, we locally suppress the superconductivity, and then the vortices are attracted to this to the position of this hot spot. And we see that we can control the size of this of this cluster just by changing the bias voltage. And I want to mention that there's no history effect of these clusters, which means that if we warm up the sample again and then perform another field cooling, then we observe vortex pattern similar to this. So no vortex clusters is observed if we just warm up the sample again. So this means the sample was not damaged by this local heating. So it's just the heating effect. We did not damage, we did not crystallize, or we did not anneal the samples. Another thing I want to mention is that our sample is a type 2 superconductor. That means that the vortex interactions are purely repulsive. So the reason why we can observe these clusters instead of observe something like this is because that there are very large amount of random pin centers in our sample. So these pin centers help us to freeze these vortex patterns. That's why we can observe that even after switching off the tunneling currents. And this is also supported by the experimental data. So if we perform a series of field coolings at the same magnetic field, and we see that each time we observe a different vortex pattern. And so this means that there exists a very large amount of pin centers, so in our sample. And all these pin centers have very similar pin strength. So otherwise, we would observe some preferential positions where the pin centers, where the vortices will stay at those places. But we did not see that. So the interaction between the random pin centers and the formation of the vortex clusters is also studied by just changing the temperature. We see that by changing the temperature, increasing the temperature, we see that the vortex cluster starts to disintegrate above certain temperatures, and then eventually we recover the original vortex patterns observed after field cooling. So now we know what happened before and after the tunneling pulse. But we don't know what happened during the tunneling because unfortunately our technique does not allow us to scan the vortex patterns during the tunneling. So in order to further understand this heating process, so our colleagues did some simulations. So by considering a local heating model, which was proposed a long time ago. So I will not go to details. I will just show you that the temperature distribution during the tunneling can be expressed by this formula, where T0 is the temperature of the sample before heating, and alpha is the parameter which is related to the power of the tunneling junction, which can be controlled by changing the bias voltage. And F function is the spatial temperature distribution, which is determined by the thermal conductivity and the geometry of the samples. We also introduced some random pinning, as you see here. So by changing the mean free path, just to mimic the situations in our samples. And we see that from the calculations, from the simulation, we see that actually during the heating, the power is big enough to heat up the superconductor to the normal state. That's why we observe this homogeneously distributed magnetic field. And when we switch off the tunneling, then these hot spots relax and form these kind of clusters, which is similar to what we observed experimentally. What's more interesting is that we have found this hotspot relaxation happens in a very short time, around 10 picoseconds. However, the formation of the clusters and the stabilization of these clusters happens in a much longer time, around 100 picoseconds. So what does this mean? So this means that the transition of this the relaxation of this hotspot is in the Kibble-Zurek regime. So the Kibble-Zurek phase transition was proposed to describe the dynamics of the order parameter when a system is cooled through a phase transition. So it predicts the appearance of topological defects and the power law dependence of the number of the defects as a function of the quenching rate. So it was first proposed to explain the universe, the early universe after the Big Bang. So where you have a lot of topological defects forms. And then it was introduced to condensed matter systems. So for superconductors, the picture is like this. So about TC, we have a fluctuating order parameter with different phases. So if we cool down the superconductor, then the domains with coherent order parameter will start to grow. And if the cooling rate is slow enough, then eventually this domain will reach the whole size of the sample. So then we reach an equilibrium. However, if you quench the sample, at some point, these fluctuations are freeze. And so this results in some isolated domains with incoherent order parameters. And the mismatch between the order parameter phases will result in these topological defects, which are vortices and anti-vortices in superconductors. And this has already been observed experimentally and in some samples. And if you're interested, you can go to these references. And from our simulations, we see that indeed there are some vortices anti-vortex pairs appears after switching of the tunneling. So, for example, as you see here, however, so these vortices and these vortex anti-vortex pairs only exist in a very short time, and then they combine and annihilate, and then disappears. So probably because the reason, and unfortunately we did not observe this experimentally. So probably the reason is that the pinning is not strong enough in our sample, so to stabilize this. So we are still working on this. Try to stabilize this vortex, anti-vortex. So, for example, by applying current through the sample, so then the vortices and anti-vortices will experience the Lorentz force with the opposite directions when we able to separate them. So, at last, I want to show you that we can use this technique to manipulate individual vortices. So what we do is very simple. So we apply a tunneling pulse at 1 micrometer away from the vortex, and then the vortices, the vortex will be attracted to the position of this STM tip, and then we apply another tunneling pulse 1 micrometer from the new position of the vortex, and then we repeat this process. By doing this, we are able to drag this vortex along this dashed line, and then to merge with this vortex. So then we observe we form something like a vortex dimer or a giant vortex. And then we are also able to drag this giant vortex along this dashed line to some new positions as one object. So what's more interesting is that we can also separate these two vortices just by increasing the temperature. Then the repulsive interactions will overcome the pinning and then separate them. And I will show you a movie that how we did it. You see that we drag the vortex with STM tip, and then it merged to form a giant vortex. And then we drag this giant vortex, and then we separate them. So by using this, then we are able to arrange the vortices to any kind of vortex patterns. Okay, to conclude, so I have shown you that we are able to use the tunneling junction as a local heater to suppress the superconductivity locally and to manipulate the vortex. And we have also shown that the quench of this hot spot of the switch of the tunneling happens in a very short time, and which place this phase transition in this Kibble-Zurek regime. This might be used to study the Kibble-Zurek phase transition in a controlled, in local positions in superconductors and many other systems. And I also show you that the ability of this STM to manipulate individual vortices, which might be useful to design some fluxing-based devices. So, thank you very much.
Thank you very much for this nice presentation. Now the session.